Hello, welcome. Let's try to solve another Leetcode problem. 95. Unique binary search tree 2. So for this one, it's going to be a little bit harder than the problem 1 because we just need to enumerate all the different cases. So for problem 1, we just need to count how many different cases, and for this one, we just need to accumulate and find all the different cases. And we are still giving an integer n. So for this example, n equal to 3, and we can find there are going to be 5 different cases, and we need to return all the different cases. Yeah, so we're going to return all the unstructurally unique binary search tree, which has exactly n nodes of unique values from 1 to n. Return the answer in any order. Yeah, we need to find all the different cases. So for this problem, we can still use a DFS. Although this n is really small, but it doesn't matter. So we're gonna still use the DFS with memorization to solve the problem. So we're gonna prepare a start and add a node. So if n equal to 3, the start node gonna be 1, and the add node gonna be 3, and we're gonna find all the different cases between this start and the add node. So the condition is that normally this start is going to be less than or equal to the end, but what happens if the start is more than the end node? So this means from here I'm going to return a none. This none I'm going to set it inside an array because I need to accumulate and find all the different cases. So it's going to be inside an array, and for this array, as I return an array, this means for example, for this node 2, at the left side and at the right side, I can put a none, and I can put a node. The value gonna be, I can put a none at the left and at the right side. So this is why sometimes inside the array it's gonna be a node, and sometimes it's gonna be none. Yeah, and for each of the node, I need to at the leaves. So for example, this leaves 3 or leaves 2 or leaves 1, 2, 1, 3. I need to give a none. So this is why from here, for the as cases, I need to return a none. And then we need to check all the different cases. So for I in range, and it is similar to the unique binary search tree 1. We need to find all the root. So which value can be the root? So it's going to be the start and add plus 1. So this means the root for the example 1, it can be 1, 2, or 3. Now we can prepare the left and right side. So if we can find the left side, how many nodes at the left side and how many nodes at the right side, and we're going to put it inside an array, and then we just need to enumerate all the different cases. So the idea is that for the left side, we're going to use start to I minus 1 because this I is the root node. So this is inclusive from the start to I minus 1. It's going to be the left side, and the final return going to be an array. And at the right side, it's going to be I plus 1 to the end. So here, this L and this R are going to be an array. And now we just need to check all the items inside the left side and items inside the right side. And this item going to be a node. First of all, let's just define the root node. It's going to be a tree node, and inside it's going to be the value, and this value is going to be I, because I is going to be the root node. Now we're going to prepare the root dot left. So this root dot left, because we prepared it's going to be inside an array, and inside array we just enumerate all the values. So for example, we just find all the items, and this is going to be a node. So at the left side, it's going to be item 1. And at the right side, it's going to be item 2. Finally, we need to put it inside the result array, and we just need to put the root value. And finally, we need to return the result. But before that, let's just define this result. It's going to be an empty array. So the idea is that, so for example, inside this example 1, we still use this example 1. So if we find this node 2, so for example, what happens at the left side? It's going to be this node 1, and at the right side, it's going to be node 3. But how can we return such kind of cases? So let's just check if what happens if there's only one node. For example, we only have a node 1. Yeah. So the start is equal to 1 and the end equal to 1. And for I in raise start to add plus 1. So this means I gonna equal to 1. So at the left side it's gonna be DFS with 1 and 0. And here DFS with this is 1 plus 2. And what is the end? So the end is 1. Yeah, because this start is more than the end. 1 is more than 0, 2 is more than 1. So definitely we're gonna return a noun. So here this item 1 gonna be a noun and item 2 gonna be a noun. So what gonna be the root node? Root node is 1. At the left side is a noun. At the right side it's gonna be a noun. And then we're gonna return the array. Inside of the array it's gonna be this node 1. This is exactly what we are doing. But this is only for one node. This is for node 1, and similarly, if we only have a node 3, it's going to be this node 3. At the left side, it's going to be none, and at the right side, it's going to be none. Now, what happens if we have 3 nodes, and we have these cases, and we're going to take this node 2 as the root node? So this is our root node. This is going to be node 2. So this is our node 2. And what happens at the left side? It's going to be an array, because this is the final return. And inside of the array, it's going to be an item. It's going to be this node 1. And inside of the R array, it's going to be this node 3. So root dot left, it's going to be item 1. So here it's going to be a 1. And root dot right, here going to be a 3. Yeah. So this is exactly what we are doing for the program. Yeah. But what happens if those 3 nodes can be a left child? Yeah. So if this happens to be a left child, it is still okay. Maybe we have a node 4. Yeah. So this gonna be inside the array, and we can still find all the different cases because this is the building block for the next one. Yeah. So if something like node 2, 1, 3, this is what we build from the left and from the right side. Yeah. Yeah, if we find a node 4, yeah, maybe this node 2 is at the left side. Maybe there are also some other cases. So all those cases are going to be inside the array. So for example, if we have 4 nodes, yeah, 1, 2, 3, 4, 5, all those 5 cases are going to be inside of the left. It's going to be inside of this L. Yeah, and this is our root node 4. And then we're going to connect it 4 with 2, 4 with 1, 4 with this one, with different cases. And similarly for the right side, we can find all the different cases. Yeah, I think the difficult part is how can we return an array and inside it's going to be none. And then we're going to enumerate the left and the right side. So finally, let me just return the DFS with the start. It's going to be node 1 and the end going to be node n. Yeah, and now let me just run it. As you can see, it works. And now let me just submit it to check. Yeah, as you can see, the past and it's pretty fast. And the time complexity is going to be start times the end. Basically, it is 8 times 8. And here we have a for loop. This is another 8. And there are also another 2 for loops. Basically, the time complexity is going to be n to the power of 5. 1, 2, 3, 4, 5. Yeah. So 8 to the power of 5 is going to be a small number. It's going to be 2 to the power of 15. That is why it's so fast. I think that's all about it. Thanks for watching. See you next time.